Last week we introduced matrices under the guise of augmented matrices, but as I told you last week, augmented matrices are just a matrix with an extra notational device. It really doesn't mean anything, but the extra notational device is the augmentation bar, the little bar down the right-hand side of your matrix that tells you that you're using your matrix to encode the data of an underlying linear system, and the bar just indicates that fact, and everything to the right of the bar is to the right-hand side of the equal signs in the underlying linear systems. But augmented matrices are just matrices. So you'll recall from last time, a matrix is a rectangular array of numbers. And our goal this week is to study matrices in a more general sense and become skilled at doing what's called matrix algebra. So our first definition today is a very easy one. When are two matrices equal? Well, to be equal, two things have to happen. Two matrices are equal if they're literally the same matrix, if they have the same size. So first and foremost, they have to be the same size. And all of the corresponding entries are identical, so same entries in the same spots. So for example, these first two matrices, 1, 2, and 1, 2, when I say them like that, they sound like they're the same matrix, but this first one is how many rows is it? It's 2 rows, 1 column, so there's a 2 by 1 matrix. The second matrix is 1 row and 2 columns, so that's 1 by 2. So they're not even the same size, therefore they cannot be equal. These next two matrices, they're both the same size, they're both 2 by 2, but if you look at the corresponding entries, they fail sort of right away. The first entry there in the 1, 1 position, row 1, column 1, is a 1. In the other matrix, the first entry, row 1, column 1, is a 3. And those are not the same entry, therefore they're not the same matrix. So what does it mean for two matrices to be equal? It means they're literally the same matrix. Here's two matrices that are equal. They're both 2 by 2, and in every single entry is the same. 0, 0, minus 1, minus 1, 2, 2, and 2, 2. Alright, so it's important to keep this in mind. When I talk about equal matrices, I mean literally the same thing, and part of being equal means same size, and all of your entries are the same. So like I said, we want to do matrix algebra, so where do we start? Well, usually you start with addition. So what does it mean to add matrices together? So the first thing you tend to want to do when you start introducing new objects in mathematics, in this case our objects are our matrices, is you start to ask how do we define some of these basic algebraic operations on them? For example, how do we define addition of matrices? And it's actually fairly easy. It's defined in the way you would expect addition and subtraction to be defined. So we can add or subtract matrices, and this is important, of the same size. If your matrices don't have the same size, you cannot add or subtract them. But we can add or subtract matrices of the same size just by adding or subtracting the corresponding entries. So here's an example to sort of illustrate exactly what I mean by that. Here I have two matrices. They're both 2 by 2. A is 1, 1, minus 2, 3, and B is 2, 0, minus 4, 7. So they're both 2 by 2, so I can actually add them together. Then A plus B is, well, before we get into it, let's just write down the matrices again. Minus 1, 1, 1, minus 2, 3, plus 2, 0, minus 4, 7. So the result is the matrix where we just add the corresponding entries. What do I mean by that? I take the entry in row 1, column 1 in A, and the entry in row 1, column 1 in B, and I add them together. So I'm going to have the matrix where my entry in row 1, column 1 is going to be 1 plus 2. 1 plus 2. The next entry, row 1, column 2, will be row 1, column 2 plus row 1, column 2, so 1 plus 0. Then down here we've got minus 2 plus minus 4. And last but not least, we've got, in the last entry, we've got 3 plus 7. And this is whatever this works out to be. This is 1 plus 2 is 3, 1 plus 0 is 1, minus 2 plus minus 4 is minus 6, and 3 plus 7 is 10. Okay, so all we did is we went ahead and we added all of the corresponding entries together to get this resultant matrix A plus B. This is easy enough to do mentally that I will never again write this middle step. Once you understand what's happening there, the middle step is just to illustrate exactly what's happening. But this is sort of easy enough to do mentally that I will, anytime we add matrices together in the future, we will just do this mentally. We'll say 1 plus 2 is 3, 1 plus 0 is 1, and so on. So there is matrix addition, and it's defined in a nice way. It's defined in sort of the intuitive way, the way you would want to add matrices together. Just add the corresponding entries. So here's another one. Add these two matrices together, 1, 0, and 3, 4, 5 minus 6. What does this equal? And the answer is immediate. It's undefined, right? And you should sort of see that, even if you weren't thinking in terms of, okay, matrix addition is only defined if they have the same size. The moment you start trying to add these together, how does this work? Okay, maybe you do 1 plus 3, but then what do you add to 4, right? It's just the entries that you have to add together, they don't match up, and it doesn't really make sense to add these together. So the answer is it's undefined, because they're not the same size. So we can only add matrices together if they have the same size. Let's do an example of subtraction. We'll let A be this matrix. It's 2 by 4. 2, 4, 8, minus 3, 0, 1, 2, 3. And B is minus 3, 4, 0, 1, 6, 8, 2, 0. And I want to compute A minus B. A minus B. Well, subtraction is defined in the exact same way as addition is. We can only subtract two matrices of the same size, but both of these are 2 by 4, so that's okay. And you subtract matrices just by subtracting the corresponding entries. So I've got A minus B, so I'm going to look at the first entry, 2, and I'm going to subtract off the first entry of B. So 2 minus minus 3. And we'll just do this whole thing mentally. 2 minus minus 3 is 2 plus 3 is 5. Next entry, we've got 4 minus 4 is 0. Then I've got 8 minus 0 is 8. Minus 3 minus 1 is minus 4. And just quickly going through this, we've got 0 minus 6 now. This entry here, minus this guy. 0 minus 6 is minus 6. 1 minus 8, minus 7. 2 minus 2 is 0. And 3 minus 0 is 3. So subtraction, just as easy as addition. To compute A minus B, you just subtract all of the corresponding entries from B from the corresponding entries in A. Now, to be fair, formally some people define subtraction in terms of addition and then scalar multiplication. So A minus B is really A plus minus 1 times B. So what does it mean to multiply a matrix by a scalar? What does it mean to take B and multiply by a number like minus 1? Well, let me introduce that now. So let me give you scalar multiplication. But you don't have to worry about that formal definition of subtraction in terms of addition by a scalar multiplication. This is how subtraction works. You just subtract the corresponding entries. But let's talk about scalar multiplication. So scalar multiplication is taking a matrix and multiplying it by a real number. So the way you do this, we can multiply a matrix by a scalar k. By a scalar, I just mean a real number. We can multiply a matrix by a scalar k by multiplying all of its entries by that number k. So pretty easy process. For example, if A is, we'll go with let's go 3 by 2. Let's call it 3, 0, 4, minus 2, minus 1, and 6. If A is this matrix here, a nice 3 by 2 matrix, then 3 times A, 3A. So I'm taking A and I'm multiplying it by the scalar 3. This is same size matrix, but I'm going to take all of the entries and multiply them all by 3. So 3 times 3 is 9, 3 times 0 is 0, 3 times 4 is 12, 3 times minus 2 is minus 6, 3 times minus 1 is minus 3. 3 times 6 is 18. Okay, so I think that's the only example I'll do. Scalar multiplication is easy enough to compute, right? You take your matrix and you multiply all of the corresponding entries by this number. So I think that's the only example we need to do. And I want to formally list some of the properties here of the way addition and multiplication interact with each other. Scalar multiplication interact with each other. So we'll formally list these properties, but they're exactly what you would expect. So I just wanted to quickly list some of the formal properties of addition and scalar multiplication. Now that we've defined these two operations, let's talk about how they formally interact. The first one is a plus b equals b plus a. In other words, it doesn't matter which order you add matrices together, you still get the same result regardless. And we have a name for this, is of course commutativity. So this says that addition is commutative, so that's nice. Next one, a plus b plus c, so you add b plus c together first and then add them to a. That's the same as doing a plus b and then adding to c, so it doesn't matter which one you do first. So addition is very nice, and of course we have a name for this as well. This is associativity, so addition is associative. And these last two tell us that scalar multiplication and addition of matrices interact in the way you would expect them to. These are nice distributivity properties. K, for example, if I do the scalar multiple of a plus b times k, well, you can distribute this just like you used to, so you would get k times a plus k times b. And the same as the one above it, so this is distributive. Tells us these two operations behave in the way you would expect, because you're used to working with real numbers. It behaves sort of similarly to how real numbers do. But where do we go from here? Well, now we have addition, we have scalar multiplication. What about, and scalar multiplication is just multiplication of a matrix times a real number. What if I want to talk about one matrix multiplied by another matrix? What does it mean to multiply matrices together? And unfortunately, the definition is not the intuitive definition. It's not just multiplying the corresponding entries like you might hope, like addition works. Matrix multiplication is very different, so let's go through this. So, matrix multiplication, how is it defined? Before we get into the full definition, I want to go through a special case, which is how do you multiply one row matrix by a column matrix? And they have to be the same size in the sense of they have to have the same number of entries. So when I talk about a row matrix, I'm talking about a 1 by n row matrix. So here's my row matrix, 1 by n. I've got n entries here, r1, r2, r3 out to rn. And then I've got a column matrix with the same number of entries, so this is n by 1, right? N rows, 1 column, so here's n by 1. And I multiply these together by multiplying sort of the corresponding entries. So I'm going to take the first entry here times the first entry here. So we're going to have r1 times c1 plus r2 times c2. r2 times c2. And then I'm going to do the third entry, r3 times c3 plus r3 times c3. And we're going to do this forever until we get to the end, Rn times Cn. What do I get as my output? I started off multiplying a row matrix by a column matrix, and my output, you'll notice my output is just a number. My output is just a number. You can think of a number as a 1 by 1 matrix if you want to, right? It's a matrix with just a single entry, but this is just a number. So this is just a real number, or it's a 1 by 1 matrix if you want to think of it like that. So there's the formal definition, the sort of abstract definition, but let's do an example of multiplying a row by a column. Okay, so here's a product I want to compute. This is a 1 by 3 matrix times a 3 by 1 matrix. So 1 by 3 times 3 by 1. I have a row with 3 entries, a column with 3 entries, so I can compute this product. And the product is defined as follows. We take the first entry of the row times the first entry of the column. So 3 times 6 is 18. Then I've got minus 2 times positive 3, so plus minus 2 times positive 3 is plus minus 6. And then I've got plus, last but not least, 4 times minus 5. 4 times minus 5 is minus 20. And this is just a number. This is what? 18 minus 6 is 12. Minus 20 is minus 8. Okay, so computing matrix products when you're dealing with a row matrix times a column matrix is not particularly hard. You just multiply the corresponding entries together and then add them all. But how do we handle more general matrices? Well, it turns out there's lots of size considerations before you can do it, and I'm going to give you the full definition now. So this is the formal definition of matrix multiplication. Again, it's much more complicated than you would hope of just I have two matrices and I'm just going to multiply the corresponding entries together. That would be great, but that's not how matrix multiplication works for underlying reasons that are fairly important. But here's the definition. There's a lot that goes into this. So first and foremost, if A is an m by n matrix and B is an n by p matrix, so they're not the same size here, right? Not necessarily. M by n and n by p, then their product A times B is the m by p matrix. So let's just cut this off here and think about this. So I've got A, which is m by n, and B, which is n by p. So in order to multiply two matrices together, this has to happen. They have to be of these corresponding sizes, which means that the number of columns of A has to match the number of rows of B. Alright, so these must match for AB to be defined. And the resultant product, A times B, is the m by p matrix. So now these two numbers, the number of rows of A and the number of columns of B, those two numbers, AB is an m by p matrix. Those two numbers give you the size of AB. Alright, so there's a lot that's going on here with the sizes. The number of rows of A and the number of columns of B gives you the resultant size of AB, and the product is only defined if these two interior numbers, the number of columns of A and the number of rows of B, actually match up. Okay, so we need all of these size considerations to happen for the product to even be defined. But what is the product? Well, AB has the following entries. The entry in the row I, column J position is just the product of the ith row of A and the jth column of B. So every single entry in AB is computed by doing the product of a row matrix times a column matrix. And that's why we just went through the special cases of rows by columns, because to compute general matrix products, you just have to do a whole bunch of products of rows by columns. So here's the formal definition. Pause the video here if you need to sort of think about this for a little while, but I think just jumping into some examples will make this a lot more clear. Okay, so we've got this problem here. Find the matrix product A times B if A is the following matrix. It's, what do we have here? 2 rows, 3 columns, so it's a 2 by 3 matrix. And it's a 2 by 3 matrix, 2, 4, minus 1, 5, 8, 0. And B, where B is 3 rows, 2 columns, so 3 by 2, it's the 3 by 2 matrix 2, 5, 4, 8, minus 3, and 1. So we want to compute the product A, B, and you'll notice A times B, these two interior numbers here, 3 and 3, the number of columns of A and the number of rows of B, they both match up, so this product is indeed defined. This is one of our size considerations we have to make. And the actual size of the product A times B would be these two exterior numbers, the two outside numbers, the number of rows of A and the number of columns of B. So I know AB is going to be a 2 by 2 matrix. So not the same size of either of these two matrices. So anyway, AB, let's see if we can compute this. So we've got 2, 4, minus 1, 5, 8, 0, times 2, 5, 4, 8, minus 3, and 1. So I know my product is going to be 2 by 2. It's going to be a 2 by 2 matrix. And I'm going to make it pretty big here because I have a lot of writing to do. But what are our entries going to be? So here I've got 4 entries that I need to fill out, right? Go back to our definition. What does the definition say? The definition says the entry right here, C11, the entry in the first row, first column, is computed by taking the first row of A times the first column of B. Okay, so C11, first row of A times first column of B. So here I'm just doing a row by column product. So how do we do this? Well, we just talked about how to multiply rows by columns. This is why we have these size considerations, by the way, because I need 3 entries in this row and 3 entries in this column for this to make any sense, but we have that. So now what's this product? Well, the first row by the first column is going to be 2 times 2, which is 4, plus 4 times 4, which is plus 16, plus minus 1 times minus 3, so plus positive 3. Cool. And that's the entry right there. We're going to do another step where we fill that out. That's, of course, 23, but we'll just do this step by step. Now this entry, this is first row, second column, right? This is C12. So how do I compute this? Well, it's the first row of A times the second column of B. So now we just have to compute this row by column product. So first row of A is going to be 2 times 5, so 10, plus 4 times 8. 4 times 8 is a bigger number. This is 32. And plus minus 1 times positive 1. So plus negative 1. And that's the entry in the first row, second column of this product. Now we're down here. Now we're in the second row, first column. So how do I compute this? Well, it's going to be the second row of A, times the first column of B. All right, the position of the entry tells you which rows and which columns you're working with. So this entry right here, second row, first column, is second row times first column. So we've got 5 times 2 is 10, plus 8 times 4, 32, plus 0 times minus 3 is plus 0. And hopefully you're getting the hang of this. Now we're in the second row, second column. So we're doing second row times second column. 5 times 5 is 25. Plus 8 times 8 is 64. Plus 0 times 1 is plus 0. And all I have to do now is simplify this. So what do we have? 23, 10 plus 32, 42 minus 1 is 41. 10 plus 32 is 42, and then I wrote 43. And here we've got 25 plus 64, 69 plus 20 is 89. So there is our product AB. In practice, again, I won't usually write this step. We will do all of this addition and everything mentally. I understand there's a lot to this, but if we don't, the process of writing down products tends to take a little while. The more you do of these, the faster you'll get, and the better at them you'll get. So you'll find that this process actually isn't isn't as tedious as it seems, right? When you can go through these row by columns mentally and identify which row and which column you're working with pretty quickly, then matrix multiplication is not a particularly tedious process. It is just a strange definition. So we'll do one more example, or actually really two, because we're going to compute both orders of these. So part A is let's compute, excuse me, let's compute A times B. So A times B is going to be 2, 1, 0, 4 times minus 3, 1, 1, 2. And we'll compute this product. Is this defined? Well, this is 2 by 2, and this is 2 by 2. So these two inside numbers match up. So yes, it is defined. And our resultant product is also going to be 2 by 2. And what am I going to have here? First row, first column? Well, it's going to be first row times first column. So first row times first column, I've got 2 times minus 3 is minus 6, plus 1 times 1. Minus 6 plus 1 is minus 5, and that's going to be the entry right there. Now I'm in the first row, second column, so this is going to be first row times second column. 2 times 1 is 2, plus 1 times 2 is 2 plus 2 is 4. Now we're down here, second row, first column. Second row, first column, 0 times minus 3 is 0, plus 4 times 1 is 4. And last but not least, second row, second column, second row times second column, 0 times 1 is 0, plus 4 times 2 is 8. Okay, so as promised, matrix multiplication is not that tedious. As long as you're comfortable with the definition, which rows times which columns, and comfortable with sort of mentally doing rows by columns, the product in your mind, then it's not that bad to compute products. But I promised we were going to do two examples with this. We've got A times B. Let's compute also B times A. So now I'm going to make B the first matrix in my product. So we got minus 3, 1, 1, 2 times 2, 1, 0, 4. Once again, this product's defined. They're both 2 by 2, and the output is going to be 2 by 2. But let's compute this. So what do we have here? First row, first column. First row by first column. Minus 3 times 2 is minus 6, plus 0, minus 6. Well, that's interesting. Notice up here I have a minus 5. So these are not the same matrix, but we'll keep going. First row, second column. First row by second column. Minus 3 times 1 is minus 3, plus 4 is positive 1. Now we're down here, second row, first column. I always sort of say this in my mind out loud to remind myself which row by which column, so the position tells me which rows. This is second row, first column, so I want second row by first column. 1 times 2 is 2, plus 0 is 2. And last but not least, second row, second column, second row by second column. 1 times 1 is 1, plus 2 times 4 is 1, plus 8 is 9. And the big observation here is that these are not the same matrix. Well, that's interesting, because all I did was reverse the order. We computed A times B, and we computed B times A. And this is weird. Commutativity says that A times B equals B times A, and that's something you're used to working with multiplication of real numbers, but it's not a property that we have for multiplication of matrices. So A times B is not equal to B times A in general. So matrix multiplication is not, in general, commutative. That's a big deal, and it's something we have to keep in mind. So it's something you have to sort of constantly remind yourself at this point, I think, because you're so used to having commutativity, working with real numbers, you're so used to not having to care about which side you're multiplying on by, because you're used to having AB is equal to BA, it really doesn't matter. But for matrix multiplication, it does. So you have to always keep this in mind, that it matters which order you do your multiplication. So in general, it's not commutative. There's other properties that you're used to seeing hold that don't. For example, if A times B is 0, by 0 I mean the zero matrix, so the matrix of the appropriate size where all of the entries are 0. If A times B is 0, well, with real numbers you're used to saying, well, that means either A or B must be 0. But with matrices that doesn't happen. Both of these can be non-zero matrices and still multiply together to give you a matrix of all zeros. Okay, so weirder things can happen with matrix multiplication that you're not used to seeing, that you're not used to working with before. So keep this in mind, that matrix multiplication doesn't have all of the properties you'd like it to have. That said, even though we don't have all of those nice properties, we don't have commutativity, we don't have this zero property, we do still have some things. Matrix multiplication is still associative, so that's really nice. If you don't have associativity, then you're working with really strange objects. So we do have associativity. If I computed the matrix product A times B times C, so multiply B times C first and then multiply by A on the left, that's the same as doing A times B times C. So we do still have associativity. And we also have distributivity, so it behaves, it plays together with matrix addition in the way you would hope, right? So if I have A times the matrix sum, B plus C, this distributes as you would hope. This just distributes as A times B plus A times C. So at least we have that. But we'll talk more about these properties, I think, 2 sections from now in 4.6. So we'll come back to this. And I just want to do one more example. So I actually want to do 2 more examples. Here's the first of 2. The question is, find this expression AC minus 1/3 B if A is the 3 by 2 matrix 1 minus 1, 2, 0, minus 3 minus 2, B is the 3 by 2 matrix 6 minus 3, 3 minus 6, 0, 9, and C is the 2 by 2 matrix minus 1, 3, 2, minus 4. So some of these that you'll see for homework, I think, it'll ask you to compute an expression. You'll have to recognize that you can't compute that expression, that because of size considerations, what it's asking you to compute, maybe A times C just doesn't make any sense, or maybe A times C is a different size than 1/3 of B, so you can't subtract them, so that doesn't make any sense. So keep an eye out for that, but I think here it will make sense. We want to compute A times C, so this is 3 by 2, and C is 2 by 2, so that makes sense. And the result is going to be a 3 by 2 matrix. And from that we're asked to subtract 1/3 B, which is a 3 by 2 matrix, so that's going to make sense. So you should check the sizes before you do anything to save yourself some work. But let's just jump right into this now. Now that we know that this will be defined, A times C is going to be 1 minus 1, 2, 0, minus 3 minus 2, times this 2 by 2 matrix, minus 1, 3, 2, minus 4, and then minus 1/3 times B, so 1/3 times 6 minus 3, 3 minus 6, 0, 9. And we just have to work out all of the corresponding pieces here. So we're going to do this matrix multiplication fairly quickly and mentally. Again, this is 3 by 2 by 2 by 2, so this result matrix is going to be 3 by 2. And what do we have? So first row, first column, first row times first column. 1 times minus 1 is minus 1, plus minus 2, so minus 3. Right, a lot of negatives there. Let me just double check that. We got minus 1, minus 2 is indeed minus 3. First row, second column, first row by second column, 1 plus 3 plus minus minus 4, so 3 plus 4 is 7. Now we're down here, second row, first column, second row by first column, 2 times minus 1 plus 0 is minus 2, and now second row, second column, second row by second column, 2 times 3 is 6, plus 0 times minus 4 is 6. Now we're down here, third row, first column, third row by first column, minus 3 times minus 1 is positive 3, plus minus 4 is minus 1, and minus 3 times 3 is 9, right, where are we? We're second row, second column, or sorry, third row, second column, third row by second column, minus 3 times 3 is minus 9, plus minus 8. So minus 3 plus 8 is, or sorry, what did I say, minus 9. There's a lot of negatives here. You lose IQ points while standing at the board. Sorry. Minus 3 times 3 is minus 9, plus positive 8 is minus 1. Here we go. Minus 2 times minus 4 is positive 8. And then minus, we'll compute this 1/3 of b. Thankfully, every single number in there, every single entry in here is a multiple of 3, so we won't have to introduce any fractions. 6 over 3 is 2, minus 3 over 3 is minus 1, 3 over 3 is positive 1, minus 6 over 3 is minus 2, and 0 over 3 is still 0, and 9 over 3 is 3. So this is well defined. This is 3 by 2 minus 3 by 2. Now we can just carry out the subtraction. And what do we have? Minus 3 minus 2 is minus 5. Remember to subtract the corresponding entries. 7 minus minus 1, 7 plus 1 is 8. We've got minus 2 minus 1 is minus 3. 6 minus minus 2, 6 plus 2 is 8. Minus 1 minus 0 is minus 1. And minus 1 minus 3 is minus 4. So just an example where we've sort of combined all of these operations together. We did a matrix product, and then with that product we subtracted off another matrix. So I want to do one more example where we multiply 3 matrices together. So here we have 3 matrices, and we're asked to multiply them together. So we're asked to compute ABC if A is this following 3 by 2 matrix, B is this, 2 by 3, B is this 3 by 2 matrix, and C is 2 by 2. So we're asked to compute this. Product, and remember we have associativity of multiplication. So it doesn't matter which order we do this. We just have to choose 2 to multiply together first. So here I'm just going to choose. Let's do A times B first, and then multiply them by C. Does this make sense? Well, this is 2 by 3. This is 3 by 2. 3 columns, 3 rows. So yes, it does make sense. The result is going to be a 2 by 2 matrix, which I can multiply by another 2 by 2 matrix. So this is all going to make sense. So we'll carry out this multiplication. What do we have? Okay, first row, first column, first row by first column. I've got 1 times minus 1 is minus 1, plus 0, so that's just minus 1. First row, second column. First row by second column. 1 times minus 1 is negative 1, plus 0, plus negative 1, looks like negative 2. Now, second row, first column. Minus 1 times minus 1 is positive 1, plus 1 times minus 1 is minus 1, so now we're at 0, plus 0, so this works out to be 0. Again, just doing this row by this column mentally in my head, adding all of the corresponding multiplications together. And last but not least, second row by second column. Minus 1 times minus 1 is positive 1, plus minus 1 is 0, plus minus 1 is negative 1. So that's the result of multiplying A times B, and then we still have to multiply that by C. 1 minus 2, 2, 1. This matrix multiplication is defined. It will be a 2 by 2 matrix, and we'll just carry out this again pretty quickly mentally here. Minus 1, first row by first column, because we're looking at row 1, column 1. Minus 1 times positive 1 is negative 1, plus minus 4 is minus 5. Row 1 by column 2. Minus 1 times minus 2 is positive 2, plus minus 2 is 0. Now we're down row 2, column 1, row 2 by column 1, 0 times 1 plus minus 1 times 2 is minus 2. And last but not least, row 2 by column 2, 0 times minus 2 is 0, plus minus 1 times 1 is minus 1. So just another quick example, doing more matrix multiplication, but I wanted to point out that you shouldn't be scared by seeing three matrices multiplied together. Just choose whatever order you want. We went A times B times C, but you could have just as well as done, because of associativity, you could have said I'm going to compute B times C and then multiply by A. The important catch here is you have to respect the order, or the side. So if you did B times C, you multiply by A on the left, right? These sides matter because we don't have commutativity here. You might, I'm not sure if there's a question like this for homework, but you might see this notation, you might see something like A squared. That of course just means take the matrix A and multiply it by itself. A cubed would mean take the matrix A and multiply by itself 3 times. And I think you'll see another type of problem where you're asked to sort of figure out what the matrix is that you multiplied by. So you have to compute the entries. But I'll leave that to you to think about. So we'll stop here. Thanks.